All right, so we're starting today with the third and final limit definition of the derivative. It's the last one for which you are responsible, okay? It's called the alternate form. So we have the formal limit definition. We have the modified form, which is the same thing as the original one, except we're plugging in a value for x. And now we have the alternate form. It is similar to the modified form in the sense that it gives you a numeric value. So it's a disposable version. But here's why it is useful. It is going to be used as a test for differentiability, which remember we abbreviate like this every day except May 15th. The test for differentiability. So remember, to be differentiable, and we did this yesterday, a function has to first be continuous if it's going to be differentiable. That means the graph has to be connected. But then, once you realize that it's connected or continuous, then the slopes have to be the same from both sides. So in order to be differentiable, it has to be connected how? Smoothly. We said that yesterday. So here would be an example of a parabola that changes into a line, and somewhere in there is where the exchange happens. This one we would say is differentiable. This one is differentiable, okay, because not only is it continuous, it's connected, which means continuously, but it's also connected smoothly. And so the slopes are merging into each other from either side. Whereas here's a parabola that changes to a line at x equals c, and this time it's obvious where it happens. This one is continuous, but not differentiable. It's connected, but it's not smoothly connected. And I'm having a hard time spelling differentiable while I'm talking. Diffable. There we go. It's not smoothly connected. There's a sharp point right there. So that's what we're going to do now without a graph. We're going to test for differentiability. What we did on example 7 is I gave you the fact that these functions were continuous, and then I gave you the piecewise derivative. So all we had to do is check to see if the slopes were the same. But the alternate form is a test for differentiability. It'll check for the continuity, the connectivity, and the slopes, the smoothness, all in one. It's a 2-in-1 test. It will on its own check for continuity and for slopes being the same. So here's what it says. F prime of c, okay, the numeric slope, it's defined to be the limit as x goes to c of f of x minus f of c over x minus c. Now this piece right here is a lot more user-friendly than in the modified form, because this looks a lot like delta y over delta x, the difference quotient. And you know why? Because it is, right? You actually see the change in two y values over the change in the corresponding x values. But instead of out front letting h go to 0, we have the limit as x goes to c. So here's why this one works. Just pay attention, you don't have to draw this. Let's say I'm interested in finding the slope of this function right here at x equals c. And here's the function f of x. So what I'm really after is this right here. I want the slope of that tangent line. The alternate form says, okay, I have to choose another point. I get that. But instead of calling it another point that is h units away from c, we're just going to say, let it equal the variable x. And by definition, x can vary. Then, if I find the slope of the secant line between the two, all I have to do is find the difference quotient, which, if this green point is the point x, f of x, and this point here is the point c, f of c, then the difference quotient is going to be f of x minus f of c all over x minus c. And that gives you the slope of the green secant line. So how does it become a slope of a tangent line? By way of the limit. So instead of letting the distance between them go to 0, we accomplish the same thing by just saying, hey, let x, the variable point that we have to use, just let it approach the value of c we're interested in. Okay? And it accomplishes the same thing. Let x get closer and closer and closer to c. That's the same thing as saying let the distance between them go to 0. It's just a slightly different way to define it. But what makes this one special then is it is a limit that is defined as a function of x, whereas the other two are functions of h. Remember, the variable that's underneath the limit is the one we're treating as a variable. So this one is much more user-friendly. It only has one unknown, not an x and an h, just an x. Okay? So I'm going to show you how to use it. We're going to do exactly what we did on example 5. On example 5, we found the slope of the tangent line using the modified form, the disposable version. And we ended up with 1/4 as an answer. I'm going to show you how to get the same number using the alternate form. Now, in the modified form, if you remember, we had h's all over the place. It wasn't that bad. It was LCM over LCM. But now it's going to be even a little bit nicer. Here's what it's going to look like. F prime of 1 is going to be the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. So all I did there is I replaced the c with the 1. I still haven't made it specific for my function yet. I'll do that on the next line. It's the limit as x goes to 1 now of f of x. Well, f of x is just x over x plus 1. Minus f of 1, that's just the y value when you plug in the 1, which gives you 1 over 2, or 1/2, all over x minus 1. So there's the setup. If you try direct substitution, guess what? 0 over 0. Hooray, you say, I set it up correctly. Now to eradicate it, we are going to multiply by the LCM, which is now 2 times x plus 1. 1 in the top, 1 in the bottom. Still writing the limit. When I distribute, good things will happen. The x plus 1s divide out first, leaving an x times 2, or a 2x, minus, and here's again where you're being a little careful, minus the 2's divide out, and we're left with minus the quantity x plus 1. But I'm going to distribute the negative now and call it minus x minus 1. All over x minus 1 times 2 times x plus 1. If you plug in again right now, you're going to get 0 over 0. So remember, your goal is to get rid of the bad guy factors. In the bottom, the thing causing the 0 is the x minus 1. What do you get if you simplify the numerator? You get x minus 1. I don't want to take a whole other line just to call 2x minus x an x. So what I'm going to do is I'm just going to group the whole thing together, because I know the whole thing is equal to x minus 1, and go, and it divides out now. And I always put a little residual 1 up there if there's nothing left. Kind of keeps me from making a careless mistake at the end. So now that the 0 over 0 problem is gone, if there is an x that's left, and there is 1, we plug in a 1 for it, and we end up with 1 over 2 times 2, which is 4. And 1/4 is the exact same answer we got in example 5.
Will you take an extra one?
Absolutely. Yeah, take as many lines as you need. So you would have minus parentheses x plus 1. And then on the next line you would distribute and maybe even write another line for 2x minus x, calling it x. That's fine. This would be the bare minimum number of lines. And as you get more and more comfortable, you can start doing stuff like this. But I will continue to say, the more things you try to do in your head, the more likely you are to make a careless little mistake. No, I should, actually. I should. I was being careless at the end. Because I started off as f prime of 1 equals, I should have the equals all the way down. In fact, what I would probably do is just bring the f prime of 1 all the way down now. So it kind of makes a little handsome gift set at the bottom. Here, happy birthday. All right. So the alternate form, it could be used just like the modified form to find slopes at a single point. It's the disposable version, though. If you wanted to find the slope at 2, you got to set up the limit and evaluate it all over again. Okay, so here's the main thing that you're responsible for after we leave this chapter. Once you show me you can set up and evaluate the alternate form, this is what you're really going to be left responsible for regarding the alternate form. You're going to have to be able to deconstruct a limit that is an alternate form and identify the function f and the value of xc, just like we did on example 6 with the modified form. Okay, so that takes us down here. It says each of the following represents the derivative of some function f of x at some value x equals c. Identify the function f and identify the c value for each one. In other words, this represents f prime of c for some function f and some value c. Same thing here. This represents f prime of c for some f of x and some c value. I'm not going to do it for you. I want you to take about a minute and see if you can get both of them. And if you need a reference up above what the alternate form actually looks like, feel free. I think you'll realize that this is a little bit easier than modified form. I hope you will. I should get used to the big book. Mm-hmm. You got it? Mm-hmm. Yeah, that's it. Okay, while we're finishing up, I'll just come back up here to the alternate form. And this one is pretty easy. If you're trying to identify f and c, the very first term in the alternate form is f of x. You don't even have to cross out anything. Say, I don't like you, Susie, or whatever. I mean, x plus 3, or 4 plus h, whatever it is. It's just right there. That's f of x, the first term. And the c value that you're approaching, take your pick where you want to get it from. The easiest place is probably right there. It's always the x value you're approaching in alternate form. So, with that in mind, it makes quick work of this. The first term is x minus 2 cubed. That happens to also be the function whose derivative this is at x equals 5. So this does equal f prime of 5. Now later on, once you learn the quote-unquote shortcut rules, you're going to be able to evaluate this without even having to expand it, and you're going to be able to then plug in the 5 and tell me what the limit is without having to use the sledgehammer method. You're going to kind of come in the celebrity door, like at Green Hall when Willie plays. There's a special door in the back called the Willie Nelson door, and only Willie Nelson goes through it. He doesn't have to come in through the front. We're going to be able to evaluate that by coming in through the Willie door. Okay? Pretty neato.
How do you identify these possibly always?
Yeah, now this one, that's a good question. Whenever you have h going to 0, that is a red flag. That means modified form, modified form. These don't really look like derivatives of functions, and so you'll always be told that in the instructions, that they represent the derivative of some function. And now if you don't see an h, you're like, haha, it must be the alternate form. There's the first term, that must be the function. And we're approaching -3, so that must be the value whose derivative it's at. And so this represents f prime of -3 for that function. And once again, once you learn the shortcut rules, namely the chain rule here, you're going to be able to compute the derivative of this very, very quickly without setting up a limit. Then you're going to plug in a -3, and you'll give me the actual numeric value of that without having to ratcon it. It'll be pretty sweet. Okay, now, the real reason why the alternate form exists is because it becomes the test for differentiability. As I mentioned, it checks for the continuity and the slopes being the same at the same time. It's a 2-for-1 test. So here's the formal definition of what it means to be differentiable at a point. Continuity at a point, limit from the left equals the function value equals the limit from the right. Differentiability at the point, all that needs to happen is the limit from the left needs to equal the limit from the right of the alternate form difference quotient, right? Here's the alternate form from the left. Here's the alternate form from the right. If they both exist and they're equal to the same thing, boom. Then the function is differentiable there, which means it's also continuous there. Let's try it out. Oh, by the way, of course, if you have the graph, it's easy to spot. You're looking for a part of the graph that's smoothly connected, for the most part, okay? Let's look at example 10. It says, use the definition of differentiability at a point to determine whether the following function is differentiable at 1. All right, so without checking for continuity first, we're just going to jump right in and use the alternate form. So here's what it would look like. From the left side, let's do that first. The limit as x approaches 1 from the left of the alternate form. So I'll just write it out first, f of x minus f of 1 all over x minus 1. That's a good way to start. You haven't plugged in for any functions yet. You're just replacing c with a 1. It's kind of a nice little waggle before a golf shot. By the way, it's National Golf Day. Now I'm going to go ahead and substitute in the numerator. the f of x that we are using from the left side of 1 is the top piece, because that's where the less than is. So we're going to substitute the piece of the function that we actually are using from that particular side. So that's going to be a negative 3x plus 1 minus f of 1. F of 1 is always defined by wherever the equal sign is, which in this case happens to be the top one as well. So what do you get when you plug a 1 into negative 3x plus 1? You get negative 2. That number, f of 1, is going to be the same on both sides, whereas the function piece, that's a variable, will change depending on whether you're approaching from the left or right.
Why did we input 1 to the f1 value but not the f of x?
Because it's f of x. We don't want it to be f. If we did f of 1 minus f of 1, that's always going to be 0. Right? That's what the definition says. It's f of x minus f of c. Yeah. So it's the variable part in the first term and the actual value on the second term. Now if we simplify, we get the limit as x goes to 1 from the left. We get negative 3x plus 3. And now that it looks pretty handsome and simplified, let's try direct substitution, huh? What do you get when you plug in a 1? 0 over 0. Hooray, you say. So we know that this is going to factor into x minus 1 times something over x minus 1 times something. If you just factor the negative 3 out from the top, you're left with negative 3 times x minus 1 over x minus 1. The x minus 1s divide out, and now there's really nothing to plug into. You get a negative 3. So what we're saying then is as this graph is coming in from the left side of negative, or the left side of positive 1, the slopes are approaching negative 3. Well, that's not very surprising if you look at the top piece here. To the left of 1 and at 1, it's going to be the line, negative 3x plus 1, whose constant slope is what? Negative 3. So it's not only just approaching negative 3 from the left, it is negative 3 everywhere. Okay? We're going to do the same thing now on the other side of 1. So we'll draw this little line here, and now the limit as x goes to 1 from the right-hand side. It's still going to be f of x minus f of 1 all over x minus 1. But as we go to the next line and we substitute in, we got to be using the f of x now where it's defined. So which piece is defined to the right of 1? The second one. So that's going to be x squared, bless you, minus 2x minus 1. So we're using that piece now. But what is still f of 1? It's still negative 2, meaning you still have to plug it in to the top piece if you're going to evaluate it. Because it is f of 1, right? F of 1 is f of 1. If it were defined by two different pieces, it wouldn't be a function. How do we find f of 1? We go to the piece where there's an equal sign. See? And because that's the only piece that has an equal sign, we still use the top piece. This is, by the way, this is how it tests for continuity while testing for the slopes. The ratios themselves are slope ratios, but by using the negative 2, which is the function value on both sides, even though the function variable pieces change, that's basically the magical key that forces it to be continuous first. Okay? If you used f of 1 on the right side by using the bottom piece, you're going to get that every function is going to be differentiable and continuous. Okay? So you got to use the same function value on both sides. Okay, so now it's all over x minus 1. If you simplify, you get x squared minus 2x. That becomes plus 1 all over x minus 1. And if you use direct substitution, you're going to get 0 over 0. So this one is a real easy factor and divide out because it's a quadratic. I know it's going to be x minus 1 times, it turns out to be another x minus 1 all over this x minus 1. Those divide out. No, wait, I meant these. Same difference. And now we plug in a 1 to what's left, and we get 1 minus 1, which is 0. So as we're coming in from the right-hand side, the slopes are approaching 0. Now the moment of truth. You compare your two values. If they're the same, the function is differentiable there. If they're different, or any one of them is undefined, it's game over for differentiability. So does negative 3 equal 0, everyone? No. So we'll say since negative 3 ain't 0, comma, f is not differentiable at x equals 1. Now, can it still be continuous? Yes, it could. Let's do that test quickly in our heads, right? The three-step definition for continuity is taking the limits of the y values. If I plug in a 1 into the top piece, I get -2. That's also the function value. If I plug a 1 into the bottom piece, I get -2. Does -2 equal -2? Yes. So here's a function that is continuous, but it's still not differentiable, and the alternate form caught it. Okay, so that's going to be a graph that looks more like this one here. It's continuous but not differentiable, right? It was connected but not smoothly so. All right, any questions on the alternate form?
You wouldn't then add on to the answer, is however it's
No, because it didn't ask for that. Now, moving forward, once we learn the shortcut rules for derivatives, you're not going to have to test for differentiability again using the alternate form. As I already mentioned, the only thing you're going to be responsible for after this chapter is the deconstruction of the alternate form and identify the function and the c value. Because the way we're going to test for differentiability in the future is this. We're going to first check to see if it's continuous, like we just did. If it's not continuous, it's game over, it's not differentiable. If it is continuous, I'm going to show you how to find a piecewise derivative very, very quickly by using shortcut rules without having to set up the limit. And then it's going to turn into a question like question 7 was. Now we'll take the limit from the left and right of f prime to test the slopes. So if the y values were the same and now the slopes were the same, now it will be differentiable. That's how we're going to do it in the future. But the alternate form, it's kind of like an old method that still works. It's a 2-for-1 method. Okay, so it's kind of nice to have. All right, the last thing that we're going to do here is just talk about this concept of locally linear. A function is said to be locally linear if and only if it is differentiable. So local linearity at a point is the same as differentiable at a point. They're synonymous. They're exactly the same. Now, here's the idea of locally linear. We live on a rounded terrestrial ball, do we not? Regardless of what Kyrie Irving thinks. We live on a globe, a sphere. It's not a flat earth. But as we walk around doing our daily chores or tasks or math homework, do we see the curvature of the earth from our perspective? No. So to us, the earth is locally flat, which is maybe why the Flat Earth Society thinks the whole earth is flat, because they're gathering evidence. Everywhere I go, the earth is flat. Yeah, okay, whatever. But we know it's curved. Unless you're at the top of Mount Everest, where you can actually see the curvature of the earth, because you have such a great vantage point, careful getting down, you're not going to see the curvature of the earth. It's to you locally flat. It's the same thing here when you have a function that is curved, the 2-dimensional instead of the 3-dimensional. If you were to zoom in on any part of that curve, if it's smoothly connected and therefore differentiable, that graph is not going to look like a curve anymore. It's going to begin to look more and more like a guess what? It looks more and more like a line, okay? And if you could zoom in then on any point on a graph and it starts to look like a line, then it's locally linear there, which means it's also differentiable. So I'm just going to show this to you on my calculator. We're going to look at the graph of e to the 5x at -1/2. And I just want to show you what the zooming activity entails. If we go to y1 and type in e to the 5x power and hit zoom 6, there's the graph of e to the 5x in blue, right? It starts off pretty flat, but then right in here, there's a drastic curvature right there because it curves up and starts increasing rapidly. If I type in the trace button and type in -0.5 or -1/2, I'll see it blinking right there. Do you think this graph is differentiable right there? Do you think the graph is smoothly connected right there? You don't think it's smoothly connected? I think it probably is, but here's one way to test. If you don't want to do the alternate form and check for differentiability, if you have the ability to zoom in, and I don't just mean like put it closer to your face, I mean physically change the scale, you can actually see if it starts to look less and less like a curve and more like a line, it's locally linear, therefore it's differentiable. So I'll just hit the zoom in command, that's zoom number 2, and I'm near -1/2. If I hit enter, Oh, there it is. It still looks pretty curvy, doesn't it? Recalibrate by hitting the trace negative 0.5 again. So there you're back on the same spot on the curve. Now hit zoom in one more time. Zoom number 2, hit enter. Can you still see the curvature? I can too. Well, let's zoom in one more time. I think I don't have to calibrate. I'm pretty much right there. If I hit enter again, I'm going to zoom in even more. Does it still look curvy? I can still see the curve, right? It kind of resembles an iPhone 6 when they first came out, right? Remember that? When you put them in your back pocket, they kind of bent a little bit. But it's still bent, right? It's still curvy. Let's zoom in one more time. Do you see the curvature there? Barely, but there's still a hint of curvature. If I go one more time, zoom in one more time. Now, all we see is a straight line, okay? And because you can zoom in at that point and it begins to look more and more like a line, we say that the function is locally linear there and therefore it's differentiable there. Now, when you zoom in and it is differentiable, you don't just see any old line manifest before your eyes, but you see the what line? That is the tangent line right there. You can think of a graph that's differentiable not being made up of a bunch of little bitty points next to each other, but a bunch of little bitty tangent lines that are so short they look like points, and if you were to zoom in, you would see the tangent line. So that's what the tangent line to the graph looks like right there. If you could calculate the slope of that line, you would find the derivative value of that line right there. So it's just kind of a neat idea. They couldn't do this back in the day before calculators. The best they could do to zoom in was just to walk closer to the graph, right? They couldn't physically change the scale. But we know we can. And so that's the idea of local linearity. And we'll call it a day right there, right?